Hola chemists! We are continuing our conversation about energy and chemical reactions, and we're going to talk about endo and exothermic reactions. So endothermic reactions are rarer than exothermic reactions, but my favorite endothermic reaction is photosynthesis. It's getting to be springtime here in the Skagit Valley, and the daffodils are first. They're out there in the field right now. They're green, they're popping up, and they are harnessing the energy of the sun, and they are storing that energy in the bulb. Exothermic reactions, the one we'll talk about is metabolism or cellular respiration, right? Cellular respiration, basically breaking down glucose into carbon dioxide and water. Burning firewood, so a burning reaction like burning the fuel in your home right now that is keeping you warm at this point is also an example of an exothermic reaction. So there are parts and pieces of the endo and exothermic reactions that are similar. There are parts and pieces that are different, and we just want to make sure you're apprised of both. One of the things that I wanted to mention that I didn't say in the last video is when we talk about energy in chemistry, it's kind of weird. We know it's measured in calories or joules, but they deem it delta H, and delta H is a change in because they can't measure it directly, and H, unfortunately, is called enthalpy because they can't even spell. So basically, when we talk about energy in chemistry, and in the last video, we talked about the bonds being broken or made between a carbon and a hydrogen, and you'll notice that it was measured in delta H, which was in kilocalories per mole. So we like to talk about different parts of a reaction, things like activation energy, things like enthalpy, and then this idea of endo and exothermic. So I'm going to basically just sort of put these side by side. One of the things that we like to do as chemists is we like to sort of graph this so we can see it as a graph. And so we're going to do two axes here, a vertical axis and a horizontal axis for an endo or exo, and then a vertical. So I have them side by side. So I'm going to basically show, oh, that looks like a heartbeat or something. Basically, I'm going to show these two reactions side by side so we can compare them. Okay, so on the horizontal axis, we're going to call this the reaction coordinate. And that's basically the course of the reaction, kind of like we start here, and that's the beginning of the reaction. And then when we get back to that, we're measuring the time basically on that axis. So this is our reaction coordinate, and I'm doing reaction RxN. And then up here on this axis, we're going to call this the delta H, the enthalpy. And so I guess I'll call it enthalpy. This is our enthalpy. Okay, so we'll put that here too, enthalpy. Okay, so for an endothermic reaction, what happens is the products have energy stored in them. So they have higher energy, so we'll do endo first. So basically when we think about this reaction, we're going to go from reactants to products. The products have more energy in them, and so I'm actually going to write them really big. So that just indicates that they have more energy. And when we look at it on the graph, we're going to put the reactants down here, and we're going to put the products up here because they have more energy. So the energy goes up as we go up this vertical axis. So that's one of the things we want to recognize. And then for an exothermic reaction, like burning a piece of wood or breaking the bonds in your food and getting the energy out, right? Our reactants start with a lot of energy and our products don't have as much. And so we start up here with our reactants having a lot of energy and our products not having as much. So what we do when we do these graphs is we actually just smoothly connect them to each other, and there's usually this big hump, some sort of hump, doesn't have to be big, in there. And we'll explain that in a second. So I'm going to show the same thing here. There's a big hump here, and then we're going to smoothly connect these guys. Okay, and again, for this endothermic reaction, let's make this green. This is our endothermic reaction. My products are up here, and my reactants are down here. And basically, when we measure this, we measure the change in the energy between the reactants and products. Delta H is the change in the energy between them. We always take the products minus the reactants. And again, I'm writing the letters to indicate the amount of energy. So more energy in the products than the reactants. So when we measure that delta H, it shows up right here. So I'm going to just sort of put that on the y-axis and the y-axis. And so this difference right here is our delta H. This difference between, I don't like it right there. Hold on a second. I'm going to put something else there in a minute. The difference between the difference between the products and the reactants. So basically this difference right here, this is our delta H. The activation energy is another sort of term that we deal with when we talk about this activation energy, the energy of activation energy. We sometimes see it as E sub A. This is the energy required to get the reaction to take place, and it's the difference between the reactants and the top of the energy curve. So basically the top of the energy curve. So that distance is going to be from here. So we're going to start here and go all the way up to the top. And that is the activation energy. And often when you talk about this, you'll see there's a activated complex or a transition substance that's there in the middle that is formed temporarily and then goes away. It's not there at the products part. Okay, so let's look at that. So the other thing we want to see here is that when we measure our delta H, when we talk about an endothermic reaction, you'll notice that because products are bigger than the reactants, we're going to end up with a positive delta H. Okay. Exothermic reactions, right? We're going to start up here. I'll make this one purple. So these are going to be our reactants. They have a lot of energy stored in them. And then our products have not so much, right? So those products are the ashes that sit in your fireplace or the waste that goes out of your body after we've removed all of the energy, right? Delta H is still products minus reactants. And you can see just by the way I do this, if I have more energy in the reactants than the products, I end up with a negative value for delta H. If we were drawing all the other parts in here, if we were doing our delta H again, we would measure the distance between the reactants and the products, right? And so our delta H looks like this, right? It's the difference again on this curve as before. This time, the activation energy is a little smaller because it's only from the reactants to the top of the curve. And basically our energy, our sort of activated complex, our temporary high energy substance, whatever's built in the middle, is there at the top of the curve, right? So this is we can call this the activated complex. Or you can call it something, it's a high energy transition state. So you'll see that different depending on your material you're reading. Okay, and I'll try to make sense of that more when we do some stuff in our lab. Okay, so we've got all of our parts there. We've got EA. I should label it those so it's there on this side too. Okay, so your job is going to be, on the next quick question, is to do this little activity right here where you can interpret those graphs for me. And then there's two little activities for you to draw and to practice that content. So I'll let you do that. And again, I'll put the answers in there as I upload those notes for you. Again, thanks for listening. Hope you're having a great day.